Yeah, let's start from AOI logic. AOI is AND or inverter logic. So remember, I know you probably haven't done that too much yet. Could you directly draw the schematic of the inverter right now? After a few lab sessions. You can?
The NMOS on top of PMOS.
No.
Yeah.
Yeah, what about Nand Gate? And why do we do that for Nand Gate? So first, how many inputs for the Nand Gate? Yeah, one output, right?
Yep.
So we need 2 transistors for each side, for 2 PMOS and 2 NMOSes. So I'm going to draw the schematic here first, and then we are going to go through about why we do that. One quick question here. Does it matter which one I shorted together? If I short these 2 or these 2 together? It doesn't matter. We'll see why. Okay, it's A, B, and this is Y. So Y equals A, B, not. So that's the Nand Gate. And why do we design the Nand Gate in that way? Why that? If you look at the truth table of the Nand Gate, what are these possible inputs? They're all of them, right?
Yep.
0, 0 is going to give you what? None. Wait. What? None. Nand Gate. Yeah. Okay, for these results, the output is 1, so which means you wanted the output pin here being pulled down to the ground or up to VD. It's not mysterious, right? We just want to implement. So this is a truth table of the non-logic. So what we are doing is just to design the circuit to implement it. Whenever we have these inputs, we need a 1. That's it. Whatever can implement that logic is good. It's a Nand Gate. So if you look at these inputs, what's the conclusion here? So what's the pattern here? Could you summarize it in English instead of logic? What's the See, you have 2 zeros, you got 1 0, or this 0, or it can be this 0, or it can be both zeros, right? So you can summarize it in English as whenever one of these 2 PMOSes have a 0 for the gate, it should be put up to the VDD. So it sounds like you need a parallel because either one is on, you can put it up to VDD, or both on, you can put up to VDD, right? So that's the theory behind it. That's why we draw them in parallel like that on the top. So either one is on, it's going to pull this one up to VDD. So these 2 PMOSes are in charge of pulling Y to VDD. Make sense? And for this one, both has to be 1 in order to turn on the channel and pull it down to ground. So sound like they have to be in series. It's like one pipe. You have to turn on both switches in order to get water flow in the pipe. So they're in series. 1 1 then is on, but however this logic is inverted. It's like an inverter because whenever these 2 are both on, it's pulling this one to ground because you have to put a 1 here to turn it on. So it's like a 1 as input. Yes, they are on, but this is being put down to the ground. The reason is we want to use NMOSes to connect the output to where? Ground, because they are good at passing grounds. That's why we put the NMOSes at the bottom and we put a PMOS on the top because they are good at passing ADDs. That's why it's called complementary MOS. Complementary MOS. That's where the CMOS came from. Now you understand, right? When so many people are talking about CMOS technology, because it's complementary MOS technology. We use PMOS on the top, MOS on the bottom. It's not just for schematic, also for the layouts. PMOSes are usually being put on the top. If you look at the MOS. Did you ask him?
Wait, oh no. Now you got me thinking about this too much. PMOS or NMOS?
Pretty sure it's MOS.
MOSFET. 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 MOSFET.
Let's see.
Amos.
MOS, baby.
Google Translate is not an engineer, that's why. She doesn't know it. So let's take a look at the layouts here. Is there what we should consider? Oh, is it? Really? Okay. So just need to turn in one lab report.
Right.
Yeah. Oh, we haven't. I'm going to cover the gates, how to design the gates today, tomorrow, and I think Friday. So probably won't be really ready for everything. But Nand Gates is easy. I'm covering today. So you should be able to do Nand Gates. And it's very similar to the NOR gates.
I know. We enjoyed the software, right?
Mm. So we'll draw the NOR gates schematic pretty soon. At least it's like half of the. Oh, so I'm gonna tell you why we do that over here, right? And then there are some complicated structures. That's the XOR gate. I'm gonna tell you why we prefer this one instead of using the gates to build the XOR gate, because this saves a lot of space. That's why I want to use AOI logic. This is what we're covering today. That's XOR. These are stick diagrams and all those things important. And that's that's the adder, is it? It's full adder. So we need to cover adder, fundamental of the adders, probably starting on Friday. So next week on Tuesday, it should be, so we do it on Friday and Monday next week. Oh, we don't have Friday, it's a short week. It's a mini break. Yay! Is it? Oh, let me see. Yeah, I think I changed it, right? So, yeah, Monday is enough. So next Monday is enough for this one. It's adequate for covering full adders. So be ready next Tuesday to work on full adders. So I think this week we're starting. What did I click? Why did I click it? Yeah, so starting from this week or tomorrow, right? You can start working on everything instead of the full adder. So here's the full adder. See, when you design the layouts, I'm showing you here, and these are the top rail, this is bottom rail, and these are PMOSes and NMOSes. And something I want to talk about here. What are these nodes? Do you still remember the name of them? What are they? Not just vias. You see they have the dots, which means the diffusion. So what are they?
Oh, yeah. It's the thing that opens up the box. No?
Yes, it is, but if you look at the schematic here, we got PMOS, NMOS, right? And that's a whole circuit. Why do we need vias? If you want to connect everything to VDD, just use metal layers. Why we need a diffusion on top? What's happening here? Mm. So the PMOS is, just remind me, what's the terminal of this PMOS? What's the terminal of this PMOS? What's the name of it? Source or drain? No, PMOS. PMOS. Source is connected to VDD, right? Drain is connected to the NMOS. So which is source, which is drain for the NMOS? Yeah, source is here, right? So you can see the source is always connected to something. Remember? What is that saying? That's a well contact. That's a body contact. When I drew the cross-sectional view, P, right? P plus, and we have a body contact. So we can short this one to VD. That's why we got a via. So what is that via? That's from N plus to metal 1. That's why you can introduce metal 1 layers. You can directly use the blue wire, which is metal 1, directly connect to the via, because the via is shorting metal 1 to N plus. Okay, so which means in electrical VLSI by default, the dots are N plus, defines the area of N plus. Okay, and you are wondering, why do we have N plus here? For the PMOS transistors, there are so many N plus diffusion as well. Does that make sense? No, which means you have dots, which means it's gonna dope the N plus material in there, right? It's gonna be N plus material. But if you zoom in, hopefully you can see it. So the slashes, these are P plus. These are PMOSs, right? So the slashes are P plus. But does that make sense? So the N plus is N plus. So the dots are N plus, right? It's N well. They are both in the N well. That's why it's N plus. They are both N material. That's why you want to put up one well for the PMOSs and the tap or the contact, body contact, putting one well. And a lot of times, if you do not have these ones, because these ones are individual components from the library, you grab them from the left-hand side from the library and drop them into the design view. Sometimes there's a gap between the PMOS dots and this. You see here? See here? Right? If you select this one and move it up, and you will see a gap which doesn't have any dots. You know what I mean? Which means they will be separated when they are being fabricated on the chip. What's going to happen is, because our PMOSs are definitely in the same N well, right? No problem. And if you keep moving that top rail up, it's going to separate the wells. So this guy, so these are two N wells, right? So you are separating the two N wells. And are we going to get an error or not? Because this one is short to VD, right? If you separate them, what's going to happen? It's not body effect. It's called latch up. Yeah, it's not even connected. So your N well here is not shorted to the highest potential of the circuit, which is the problem. So sometimes you want to pay attention to it. If you move this up, there's no overlap between these two N wells, then you are getting a problem. Okay, so what's another way to solve that problem? in the library in electrical VSI, there's a component just called probably pure N diffusion or something, just pure diffusion, N type,
I think it's called
pure N something, and just dots. You can see there are just dots. And you grab that one and place it in the view, and it's going to be by default it's a little square. And you right click and redefine the size of it and just make it big, right? And then cover it. You know what I mean? So just make it big enough. Even though you have gaps here, you have little corners, it doesn't matter because you just define the whole area and put them in the same and well. Feel free to overlap with everything here. And now you'll see the benefit of putting all the PMOS on the top. Right? So you can directly draw a huge rectangle or a box and cover all the PMOSes and put them in the same well. Make sense? So it's just better organized. So the PMOS on the top, you just cover everything, including all the body contacts. Just put everything in the same diffusion. And I think we haven't done that, but there are 3 types of checks. One is DRC, another one is called NCC, right? But NCC is really odd name. It should be LBS. It's layout versus schematic. It's called LBS in any other tools, right? Keep in mind it's LBS.
What is it?
I don't know. Yeah, it's LBS. And there's another one, I think it's called well check or something. The well check is checking if you have the good well contacts, or if you put everything in the same well. Or if you have for example, these two, right? If you pull this up, and there will be a gap, right? But by the designing rules for C5, I think the distance between these two wells must be larger than something. However, if you do not overlap these two, have a very small gap, you have to zoom in for 10 times in order to see the gap, which means the gap is tiny. But the pro size, for example, is 500 nanometer technology. The smallest size they can fabricate is 500, for example. And the size between the two wells is like only 1 nanometer. It won't pass, right? Because the tool or the foundry is thinking like, you really need a 1 nanometer gap. But actually you won't be able to. So actually they will be overlapped, but it's an error being seen as a foundry, right? That's a problem. So you can just, in order to avoid that issue, just directly draw a huge box to cover everything and put all the PMOSes and unwell contact in the same unwell. Makes sense. Same for the NMOSes. See, NMOSes are in where? The slashes, right? It's very interesting because the NMOSes are directly in the P sub. You guys are saying NMOSes are being fabbed in the P well. Sometimes they are called P wells, but you don't really have a P well. It's just P sub. It's P type substrate. That's how they label it. Instead of just drawing nothing, they draw all the slashes like that as a P sub. And if you zoom in, you can see, are these NMOSes or PMOSes? NMOSes. Do you see the dots? Right? It's the dots, right? So dots means these are N-type diffusion. And I can see that the dots are something like N plus or N wells. Slashes are even are either P plus or P sub. Okay. Same here. If you want to avoid all the well errors, just directly cover everything to the P sub layer. So for the Nand Gate logic, the 2P parallel PMOSes can cover all these logic, input and output, and the 2 NMOSes in series can cover this logic here. So this circuit serves for this true stable. So that's why this is a Nand Gate.
The body on the first NMOS, do we give it its own ground contact, or can we just short it straight down?
Yeah.
Okay.
But this one does have a body effect because the source is not shorted to the
Right.
body contact. It has a higher threshold voltage, but it doesn't matter since these are either 0 and 5. Can always turn it on or off. No problem. 1 volt logic, which means you need a different transistor. So the 180, I think the ideal operating voltage for 180. Oh, can we see that? I couldn't disclose it, even though it's a very old technology. I couldn't say too much about it. You haven't signed the NDA. I have the NDA, but you haven't. Huh? With TSMC. Yeah.
Oh, why did you sign an NDA for the foundry?
It's not. It's yeah. Even though I mean it's 2005, 17-year-old technology. It's still being used a lot.
Oh,
So the 5. So this I can disclose this is the cost of it. So for example, the TSMC 180 from Muse, right? From Muse. This is one of the most popular MPW company, multi-project wafer, and it used to be Moses was the most popular one, but it's a non-profit. That's why it's not working anymore. They were able to do C5 for us for free by 2018. I think they have been doing that for over 20 years for every single university. When I was in graduate school, every single one in my group have submitted chips to Moses for free. It's usually C5, but a lot of times if you want to request it for newer technology, just request a PDK, the personalized design kit. I think pretty much for everything, for everyone, not just C5. You request it, you install it in the local server, and you're able to do a design and fabricate it through Moses. Have to apply for a grant, but it's not actually you're not getting any money, but they will just tape out the chip for you. It's not functioning anymore. For C5, I think the lowest cost to fabricate any C5 chips is $27. 500 nanometer technology, whatever. Even you put
is
it.
it a good thing for us that Moses doesn't exist anymore?
Why? No.
Because if we still have the opportunity to make a chip, but nobody else has the opportunity to make a chip, then doesn't that make?
No, it's $27. It's too expensive. It's hard for us to afford it actually. So in the past, back in 20, I think we got lucky, because I do need many dies to test our wire bonder, which is very rare equipment we can own here actually. And a lot of other ones they don't even have it. So in order to test it, we need a lot of dies. So we received the dies from my analog class in 2018, and so every single one in the class, I think I got like 20 something students in the class. Every single one have a different design, and we submitted to Moses. We got a chip, so 5 copies for each student, 5 dies in the little box, and about 5 dies being wire bonded in the package for free. Already wire bonded for free. You got a chip, you test it, it worked. So the little op-amp works really well. The yield is really high because this is a huge technology, really, really old and reliable. Yeah, now it's 20K.
Making the chip can't be that expensive.
It's more expensive than that actually. The reason they can reduce the cost to 20K is because they are a multi-project wafer.
Right.
They put your design probably, even though we multiple designs, so we are probably only using this much of the wafer. It's a 15-inch wafer. Okay, we're only using this much of the wafer, and all the rest of the area is being used by TI or any other company who are going to design fabricate something. Right?
Why are the wafers always
Yeah, that seems impressive.
They spin coated, right? If it's not a circle, then it's gonna oscillate or something on the spin coater, I guess. Have you spin coated? Yeah, you have. Yeah. Yeah. So the chips in these areas are most faulty ones. The yield here is low, yield here is high.
So the yield in the center is like pretty much
I don't know.
the whole wafers.
I think so. I mean, but for even TSMC, for the overall wafer, it's still over 99%.
Yeah.
I think you're right. So these ones are probably somewhere around 100%. Yeah. So again, come back to this one. Right now, we do not tape out the chips with most of them versus $27 at least, but they can do somewhere around 6K for 180, and we're getting 40 copies of the die of the design. 40 dies. Same. How they run the business, we don't know. It depends on the cost of running the business. Yeah. And whenever it gets down to, I just saw the table today, I guess 28, I forgot. It's still from TSMC. And this one is 13K, if I'm right. It might be more expensive than that. Or 130, I forgot. It's very expensive. I remember the next level, I think it's somewhere around 90 nanometer technology is already over 10,000. So I think this one is probably 130, not 13K. See, the bar is high. You can learn how to code at home just watching the YouTube online courses. You couldn't fab a chip by just learning and doing at home. The bar is high.
Oh.
Yeah,
It's just at the moment.
Some spray bottles. Doping materials.
what about NOR gate? You can figure out NOR gate. What's the logic here? 0, 0, 0, 1, 1, 0, 1, 1. NOR gate or not, right? Or it's going to be 0 here. Wait, oh, 1. 1, 1, 0, right? Or 0. So which means in order to sort it to VDD, you have to turn on both PMOSes. You have to turn on both PMOSes in order to sort it to VDD. Is that correct? Have to be 0 at the same time. Yes. Yeah. Does it matter which one being shorted which one? No. Here's the output. More.
This makes so much more sense than when I talk here.
Yeah.
Speaking like these are like, this is the hardest part of the whole semester.
Yeah, it is. Students right now in that class is also struggling. It's okay. Couldn't be easy for the whole semester.
It eases up after the gate section.
Yeah, I believe that's the only module has circuit related stuff. They haven't learned circuit 1. That's why it's not making too much sense. So you'll see all the issues of the incorrect connections.
Yeah. I think it took me like 3 or 4 hours to get a NOR gate in LT Spice.
Oh. Yeah.
Because I had it.
Yeah.
And I had some arrows where they like weren't flipped correctly, so it was going the wrong way.
It is. Yeah. And the most common one is they just short this pin to here.
Oh, yeah. Like, yes, you're always going to have
Yeah.
positive one.
Yeah, yeah.
Oh.
Okay, so this is simple. Okay. What about XOR? XOR. God, XOR is different. XOR is a little bit different. XOR is A not B or A B not. So the first way to build the actual gate is just using gates. So the AND gate, OR gate, and NOT gate, right? You have A, B. So this is A, this is A NOT. B, this is B NOT. So I have A NOT B, like these two. AND logic, A B NOT. AND logic, and these two, OR logic. So this is A NOT B or A B NOT. How do we design the layout for the NAND gate before we move forward? Figure that out first. What about the layout? If we, so for PMOS, okay, I think what we use for the PMOS is cross. So these are the two PMOS contacts. And here's a channel, and here's a gate. Yes, a diagram.
So that's a PMOS?
Yeah. Doesn't matter as long as you, I think this is what I used for the, yeah, for the lab. Yeah, just want to make it consistent. You'll see. A lot of times you have to draw the sig diagram first before you move to the real layout. This makes it a lot easier. So for the PMOS, two PMOS on the top in parallel, how do we do it? Two PMOSes, right? You got one, you got another one. Here's the top rail, here's the bottom rail, right? I got two NMOSes. Connect. So these two are in parallel. How to connect them? In parallel means, let me see how I do it. I think there are a couple ways. You want to make you want to optimize it. Which one is a better way? Let's try the both ways right now. We'll see which is better. Okay. So first, so the drain source stream, whatever. Okay. If I short these two together and do that, so current flows here and being split into two channels and merge here. Those are in parallel, right? And these two are in series. Do you want to pull this wire and connect the middle one or connect to one node? One end, right? Make sense? Okay, then what about the gates? Remember, it doesn't matter which one connect to which one, right? Do I want to connect here to here and here to here, or just directly draw a straight line? You like that shape? They are in the same layer, which is polysilicon layer. They are going to being shorted to each other, right? So since you just do that. Oh, you want to go up and go to metal one? Okay, so does this make sense? Okay, I don't have too many colors here, but now you know that these are polysilicon. What about these ones? Metal one, right? Okay, then what's next? I need to introduce the input to the left, which is what we usually do. Could you use a poly? You can, but usually you see here's a drawback of this structure, because if I use a poly to do that, that's too much poly, too much resistance. So this is a problem, right? Because this is shorting to this poly. And now you're thinking, hey, let's go up to metal one. I'm gonna get a via here, directly introduce a via, and get a metal one, then short it. So the initial design here is not really optimized. It won't be an issue. You can go up to metal 2, yes, but there's a better way to design it. See? What's a better way to do it? So what if I do this? So this is the same node, right? This is both from the same voltage. And then flow and split. What about that? Then if I do this, and poly, is there shorting together? No, it's poly and metal 1. Then what? I can do a poly, I can do a. So usually you still have to connect to metal 1. You don't want to introduce too many, because the poly needs to be shorted to other metals. So usually right after that, just beside the poly layer, you need a via to metal 1. You know what I mean? That's what you usually do. You'll see in the lab. So you introduce metal 1 just beside that poly, so you are not using a too long poly wire. You just use a metal 1, which will reduce the resistance. What about this one? As long as you're comfortable with the length, just look at it. As long as you can use more metal, just use more metal. There are always trade-offs in between, the layout, efficiency, and also the lengths of metal and poly. You just have to. So, for example, here, I don't have to use any long poly. So right after it, I just introduce a via to metal 1. Compared to this one, it's a lot better, right?
Yeah.
Solves the problem. You don't need to route all the wires to a lot of places. So if you route it here, then this is just one cell. You have thousands of the same cells. You're introducing more risks to short to other cells. Make sense? Still not the best. I mean, the routing is okay, but like this one. So I have a via going to metal, go to another via. They are the same voltage node, right? Do I need the 2 vias and metal?
No.
So what you can do here? So what actually we do is just 2 diffusion nodes, just 2 N pluses, N plus 1 and 2 N plus. And remember the length of the channel is defined by what? The gate, the size of the gate. Okay. So you can reduce the size of the transistor by deleting that middle via. Let's see if we have an example here. See?
Oh, that's what that is.
How did you make it? Like, oh, so these are the parts available in the library, right? Like the NMOS, but the NMOS doesn't have that via, does it? No, no. You have the via as a separate component.
Yeah, we have to.
So you grab the NMOS, you grab a via and resize it, and then connect them using the green wire, which is diffusion, and then you move them together to make an NMOS, right, on both sides. But when you are making 2 NMOS in series, you don't add a via, via diffusion to metal 1 via in the middle. but you directly connect them using the green wire. Now it makes sense why you do that, right? They are the same node. Why bother adding another via? Just short them together. So the question is, why we need that thing here for the PMOS? Yeah, that's right. Yeah, because you need to introduce a wire in the middle. You need to introduce something in the middle on the metal 1 layer. Here, you don't need to introduce anything here, right? It's just something internally, right? Since you need to connect it to somewhere else, that's why you need a via in there to connect to metal 1. Here, there's nothing to be connected to the middle here. That's why I just directly ignore it. So whenever in the future you're not using any of the 2 nodes, you can directly ignore it or delete it. But I have to do it here because, yes, they're in parallel. That's why you need a wire in the middle. They're in parallel, right? So you can simplify the bottom transistor like that. What about this one? Can you simplify this part as well?
No.
Think about it.
Yeah.
Do really? Yeah. Just got one. You just need one connector, right? Just remove this one. One of the vias. See if I did it here. See? Okay, I just removed one. I just need a one to make one metal 1 trace to connect to the middle. So that's the optimized Nand gate. 2 NMOSes on the top that have a middle contact, and 2 at the bottom without any middle contact. So what I did is I connected these 2 nodes to VDD and introduced the middle layer here, and I put an A here. Why put an A here? I should put it on the left, but that's okay. So that's output, right? It won't, cross the metal 1, actually. Yeah, poly over metal 1, yes. So I think what I did in the larger scale design is, so here, the reason that I cannot place this one here is because this is a poly to metal 1 via, so it has both poly and metal 1 in there, material in there. You can see, because I want to make the gate compact, so I don't have much space. Like these stick diagrams, these are just some fake design on the paper. So the traces are super thin. So I have a lot of space here, right? But in the real design, I really don't have that much space. I don't have space in the middle to place a via in there. This metal 1 is going to be overlapped with the via's metal 1. So I have to do it on the right-hand side. But in the future, what I can do is, or what I did, okay, for the larger scale design, is whenever you see an error, remember you will move it, you just move it as close as you can, and at some point you will see an error. Okay, then you stop and then move it back. So that will be the smallest gap you can have. So what I did, I guess, is I introduced a metal 1 to here, very short metal 1 trace, and I built a metal 1 to metal 2 via, right? And then I put a metal 2 to here. And then metal 2 to metal 1 for this one. No, you don't have to go down one step, right? So these are A and B, but both in metal 2. Like that. That's what we did, I guess, in the lab. All right. So what about NOR gate? Very similar, right? NOR gate. So this is Nand NOR. Let's just directly draw the optimized version of the NOR gate. You have 2 PMOSes on top. Do we need any diffusion in the middle? Mm-hmm. Right? We only need one. Remember, the better version of the parallel transistor is introducing two wires on the two sides. And here's the middle one. Right, it has to be shorted to here. Two polys. According to the layout I just had on the website, I think what I'm gonna do is directly introduce the metal one via, and do I have space here?
Loads of space.
Let's see.
You totally had space on that.
Okay, so this is what you are going to have. So no space, because these two are too close to each other. So the poly layers are too close to each other. You have to draw it that way and introduce another input over here. So you can directly draw a metal 2 via here and then introduce the left-hand side. Same here. Okay, I have the both input on the left-hand side and output on the right-hand side. Okay. So what about the XOR gate? This one. If you don't optimize it, what you're expecting, a lot of transistors. Now let's see if we can go through it. So first you have inverters and AND gates, right? How to draw an inverter? Like that, right? And this is A, and this is A naught. And this is B, and this is B naught. And the AND gate is a NAND gate in parallel, right? I'm not using different color here. One you can just have more of them, and this has to be shorted to an inverter. So this is the AND gate. This is the AND gate, right? And you got another AND gate. Here. Another AND gate, and you need an OR gate. OR gate is these are all the gates you need. Let's make the connections. I'm not consistent with the colors. Sorry for that.
Oh my.
A, B, A naught. Wait, so A naught and B are going through this the first AND gate. A naught and B and then A and B naught. Oh. And these two are ORed. So that's the XOR logic.
Transition for that.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 22.
All right, let's see how big then.
Now you see why do we need a stick diagrams?
Yeah. Yeah.
Because you open up the layout and you just look at this guy. Could you lay it out? No. You
I
want
don't
to
know if I could lay it out with that. You think?
just this, right? You
No,
couldn't.
even with this.
Oh, even with this one. Yeah, so you draw these, I highly recommend you use a different